In this video, we're going to look at another acceleration example. Here the problem says, a car starts from rest and moves along a straight line with an acceleration of a equals 3x to the negative 1/3 meters per second squared, where x is in meters. Determine the acceleration of the car when t equals 4 seconds. So I'm actually going to start off by showing you what not to do. So it's very common for students to say, oh, well, I know what acceleration is. I know acceleration is equal to dv over dt. So then they plug in 3x to the negative 1/3 is equal to dv over dt. They move the dt up here. They say 3x to the negative 1/3 times dt is equal to dv. They integrate and they say, oh, x is not changing with time, so then they just say 3x to the negative 1/3 t is equal to I should say from t naught equals t to t, from v naught to v is equal to v minus v naught. This would be absolutely wrong. Do you have any guesses why this doesn't work? The reason this doesn't work is because here you've assumed that x is not changing with time. And even though here this x value is not the integrating variable, x is changing with time. It's implicitly changing with time. And so we actually have to start off with a different acceleration equation. So now let's try using acceleration is equal to v dv over dx. Now we'll plug in what we know for acceleration. We'll move the dx over. We have 3x to the negative 1/3 times dx is equal to v dv. Now when I integrate both sides here, so then we end up with 3x to the 2/3. Oh, I forgot to put my limits here. Put the limits evaluated from x naught to x. Divided by 2/3 is equal to v squared over 2 evaluated from v naught to v. If you simplify this, I'm going to move this up. If you simplify this, you end up with velocity is equal to 3x to the 3rd. Now, the question was asking us the car's acceleration when t is equal to 4 seconds. This equation doesn't have any information about t. There's no t variable in this equation. So we have to figure out how to include it. And how would we do that? Well, we know that dx over dt is equal to v. So what if we replace our velocity with this derivative? So now we'll say dx over dt is equal to 3x to the 1/3. And then we'll move these around. So we'll bring dt up and we'll bring this down. So then we have, we'd have 1 over 3x to the 1/3 dx is equal to dt. Now we can integrate both sides again, and we end up with, this goes from t0 to 0 to t x naught equals 0 to x. So we end up with 1/3 x to the 2/3 divided by 2/3 equals t. If we rearrange this, we end up with 2t is equal to x to the 2/3. Now, the question was asking the acceleration when t equals 4 seconds. So now we plug in 2 times 4 seconds equals x to the 2/3. This gives us a value for x equals 22.6 meters. Now, if you're not sure how to get the x from this equation here, make sure that you go through the math of that. You have to use the natural log to solve for x there. But the question wasn't asking us for the position. It was asking us for the acceleration of at that time. But our acceleration equation is in terms of x, so I'm just going to move this up. So we know that acceleration is equal to 3x to the negative 1/3. So if we plug this x value in, we end up with acceleration is equal to 1.06 meters per second squared when t is equal to 4 seconds. This question really highlights that sometimes the solution path is obvious, sometimes the solution path is not super obvious. And I'm going to write this down. Sometimes the solution path is not obvious. So you have to really ask yourself, integrate with respect to what? Differentiate with respect to what? To what variables?